If I use some energy and hit this piece of paper with a pencil, you can see that the pencil passes through. If I don't use as much energy, you can see that the pencil does not pass through. This is obvious, but is it? As it turns out, the phenomenon of quantum tunneling tells us that on a quantum scale, this question is not so simple.
In quantum, positions are probabilistic. This is because a particle also acts as a wave. A particle has a definite position, but a wave can be in multiple places at once. We represent the probability that a quantum object is at a specific position with a wave function. The probability is found by taking the square of the value of the wave function at that position, and the wave function is normalized to have an area of 1. When a particle encounters a potential barrier that is higher than its total energy, classical physics predicts that the particle cannot pass through the barrier. However, the Schrödinger equation shows that the particle's wave function does not abruptly drop to 0 at the barrier. Instead, it decays exponentially. This means that there's a non-zero probability that the particle can end up on the other side of the barrier.
This almost sounds like magic. Are you sure this is possible? My answer to that is yes. This is because without quantum tunneling, the sun would not shine.
In order to generate light, the sun relies on a process called nuclear fusion. Nuclear fusion occurs when two light atomic nuclei form a heavier nucleus, which releases a significant amount of energy. However, electrostatic repulsion acts on the two positively charged protons in the nuclei, separating them. But as this happens, quantum tunneling allows particles to pass through the potential barrier and allows a strong nuclear force to take over and bind the nuclei together.
Quantum tunneling has so many applications in other fields as well.
In computing, quantum tunneling is used in flash memory to store data. In biology, scanning tunneling microscopes use tunneling to scan surfaces at an atomic level, allowing for things like DNA mapping.
And all of this together makes quantum tunneling incredibly exciting.